First of all, any questions about the project proposals? The project proposals are due on Thursday. We need them to get in on time because we want to grade them over the weekend and get them back to you so we can get feedback to keep working on them afterwards. Any questions about any of the projects or about what is needed? The proposals are relatively short, but I do want them to kind of show, some evidence of what you're thinking, what you're planning on doing. Some evidence that you've started working on it is good. Okay. On my webpage, I have examples of projects, proposals from previous years that were good. Any questions about that? Okay. Is there anybody still looking for a partner? Okay. If you're looking for a partner, I might be willing to try to broker with you, but I do encourage people to find a partner. Any questions on the projects? Okay. So what I wanted to talk about this week are linear models for classification and regression. And I like linear regression. I know many people may feel that it's an old-fashioned thing, but it's good for making models that are interpretable. It's good for explaining a lot about how more complicated models get trained. And it's good to kind of know what the limitations and how you can work around the limitations of purely linear models. So this, I think, is kind of an important thing. So what is we've talked about before, linear regression is finding, given a collection of variables y, values y as a function of x. Here x is one variable. In general, it can be d variables. Okay, we want to find the line that goes through those points that best fits the points. Okay, that's linear regression. Now, why do we like linear functions? Linear functions are easily understood. In many cases, they are a reasonable thing to want to do. Okay, often things grow linearly with a variable. Again, nothing in the world is really truly linear. So if you really want something to be linear, you should only measure it at 2 points. Okay, but in general, linear functions are good. Now, one thing that I find when I think about what makes linear regression easy or hard, this is maybe one way to look at it that might be interesting. If I give you n lines, if I give you the equations of n lines, and I ask you to find a point that goes through those lines, that sits on all of those lines, how do you do it? What is that called? If I give you a bunch of n lines, okay, and I want a point that is going on that, what is that procedure? Have you ever tried to do that before in your life? Okay. Yeah? A unique solution for linear equations. When you took Gaussian elimination, what is it that Gaussian elimination did? You were given n equations, probably 3 on your homework when you did it in high school, and you were said, find the values, okay, of a point that was on simultaneously on all of those lines. Does everybody agree that's kind of what you did then? Now, what is the problem of, suppose I ask you, given n points, find in d dimensions, find the line that they all lie on. Okay? Is this an easier problem or a harder problem or exactly the same problem? Okay? I now give you n points in d dimensions, and I ask you, find me a line that goes through all of those points. Okay? It turns out it's the exact same problem. Okay? And I'd like to convince you of this by the idea of what you would call a duality transformation. So in a duality transformation is in 2 dimensions, which is what I'll show you, is a mapping that takes points to lines and lines to points. Okay? So if you have in 2 dimensions, a point has an x coordinate and a y coordinate. Does everybody agree with that? And in 2 dimensions, a line has 2 parameters, a slope and an intercept. Right? Now, what if I did the transformation where for every point st, I interpret it as a line s times x minus t. Okay? And any line I interpret as a point st. Okay? This gives me a way to transform points to lines and lines to points. Does everybody agree with that? May not seem that it does anything, but certainly by definition this is a mapping of lines to points. What's interesting about this? What's interesting about this is here on the left I've got a picture of one point that lies on 2 lines, okay? And I've got 2 points that are on each of these 2 lines. Does everybody kind of get that idea? What should happen if I did a duality transform of these, this situation? My red point is going to become a red line. My blue lines, my blue and black lines are going to become blue and black points. Okay? And if you notice, here over here I have 2 lines on a red point. When I take the duality, what I get are 2 points on a red line. Okay? The magic of this duality transformation is that it kind of preserves the identity of this thing. What is going to happen to these 2 points? Okay? These 2 points have the property that they are on the blue line. The blue line is becoming a blue point. The blue points, okay, are going to become blue lines, and they go through the point corresponding to the line they were on. Does everybody kind of get this idea? Okay. So by observation, this is not, I haven't given you a proof, but but the observation here is that if you have lines that are on a point, when you dualize it, you get points that are on a line. By solving linear systems, you can, you can find where is the point that is on all the lines. If I dualize it, that problem becomes, is there a line that is on all the points? So if you believe this, then in fact the problem of finding a line on all the points is exactly the same as the problem of finding the point that is on all the lines. Okay? Any questions about that? So what is the part that makes linear regression a hard or an interesting thing? Okay? Really, the only thing that is challenging to us is the little red quotes here. Okay? With linear regression, we're not looking for the line that goes through exactly all the points. We're looking for the line that best goes through all the points. Okay? Any questions about that? Okay, good. So what is the story in linear regression? We measure the quality of a fit, a linear fit to our points, by the residual error. Okay, if I have a line that is supposed to model this, for every point xi, okay, given the parameters of my line, I am going to come up with an estimate of where that point is. The difference of the real y from the predicted value from the line is the residual. Okay? And what we're going to be interested in is generally which line minimizes the sum of squares of the residual errors. Okay? And why do we care about this? Well, one, sum of squares gets rid of the sign problem that a positive error is as bad as a negative error. Okay? And because there is a nice closed form here. Any questions? Okay, that you can believe. Now, as I mentioned, there is a closed form solution, okay, for solving linear regression problems. Okay, it is if we have a system of here our data value, okay, A is going to be our matrix of data points, the x values. B is going to be the vector of target variables, the y's. W is going to be the coefficients that you want to represent each dimension of A, each one of the columns of A, okay, so as to best approximate B. And as we said before, the weight matrix is going to be the inverse of the transpose of A times A transpose times B. And if you work through the dimensions of this thing, the weights are going to be an m by 1 vector. Okay, m is the number of columns in the data matrix A. Any questions? So if you believe this, okay, this says least square optimization is basically a problem of matrix inversion and multiplying matrices. Yes?
Yeah, I think you explained this in the previous class, but let's say AW equals B, and then we multiply by A inverse. So W becomes A inverse B. So how is A transpose A the whole inverse?
Wait, say that again?
So let's say we multiply on both sides by A inverse.
A inverse, right?
So W becomes A inverse multiplied by B.
Yeah.
So how is this term that's A transpose A the whole inverse and A transpose B coming?
Well, if we say that W, if we multiply both things by A inverse, then we're going to say, okay, wait, I'm not getting the question here. Let's try one more time. So we certainly agree that just as a linear, if we have A times W equals B, if we multiply both sides by A inverse, that's going to say W equals A inverse times B. Okay? Right? And this is an argument that what this would mean, if you think about it, is that that if you had a different value of A, okay, then you would end up getting a different values of B. It would lead to a different value of A. Okay? So this would conceivably give you a way of coming up with the weights of this that would equal that. Okay?
So but the equation on the...
Okay, I see what you're saying. You're saying, why is this different than that? Okay? So this is assuming, let me just think about it. This is assuming equality. Okay? And this is assuming the weights that will minimize the least squared errors. That's what the difference, that's why they're two different expressions. Okay? Any questions? Now, where does this thing come from? Okay? We'll talk about that in, actually, I thought yeah, okay. Yeah. Well, we'll talk about that in a minute. Okay? Where does this thing come from? But what does it reduce to for linear regression when we consider it in one variable? This turns out to be kind of interesting. Okay? In this case, we're seeking the best line, intercept W0 times slope W1 times x. If you work through what the slope is, the slope comes out to be x minus the mean, the sum over, as I goes from 1 to n, of xi minus the mean times yi minus the mean, divided by the sum of x sub I over the mean squared. If we look at this, does this look familiar? Okay. What was the correlation coefficient? Remember how we had a formula for the Pearson correlation coefficient? What was the Pearson correlation coefficient? It had the same numerator as this, but it was normalized by the standard deviations of the two, correct? Now, what is this? This is the square of the standard deviation of x, okay? Actually, no. This is the standard deviation of x, okay? And so what we should have is the correlation here the correlation between x and yi would be the numerator divided by sigma of x divided by sigma of y. Okay? Sigma y doesn't appear here, so we multiply the top by sigma y. Bottom line is the slope here is going to be proportional to the correlation and the standard deviations of the x and y variables. Okay? The slope is going to be how well does it fit the the underlying data. If we multiplied all the points by 100, the correlation would be the same, but the standard deviations would be a lot larger. These will represent the kind of scalings, okay, to work on the slope. The other thing about the linear regression solution in one dimension is that the best fitting line always passes through the centroid of the points. So when we have a slope and the centroid is the average x and the average y, this gives us a point, and the slope between that's enough to fully define the regression line. Any questions? Okay, good. So what does this mean? If we have a world where x is uncorrelated with y completely, then the slope should be 0. If if x and y are perfectly correlated, okay, then the magnitude of the slope, the observed slope, will depend upon the magnitude and spreads of the points, okay, which is basically given by their standard deviation. Any questions? Okay. Now, where does this formula for the weights of the linear regression formula come from? Okay. What is the case is that we're looking for the weights that will minimize the sum of squared error. Okay. The error vector is the real values of the y's minus our predicted values, which is a times w. This is going to give us a an error vector, the important thing is that the error vector has to be orthogonal to the vector for every variable, because if not, there was a way you could improve, the fit by moving adjusting the weights to make it orthogonal. So what does that mean? That means that the error vector, is going to have to be, when two vectors are orthogonal, the dot product is 0. That means that, if B minus AW is going to be orthogonal, it's going to be the dot products with the transposed matrix are going to be 0. Once you have this and you do algebra, you get the equation. So that's kind of where it comes from. Any questions? Okay. Now, on your homeworks, you've had to make a couple of regression models. In general, how can you make regression models better? Some of these I think you may have done on your homeworks, but there are a few standard techniques that are useful in fitting regression models, and also with other machine learning paradigms. One is to note that if you remove outliers, you can dramatically improve the fit of a linear regression model. Here we have a case where there are a bunch of points that are well fit on a line. There is one outlier. Because the punishment for the outlier is that we pay the square of the residual for it, the line is going to chase the far outside point to try to minimize that sum of that squared term. So you end up getting a line that kind of chases the outlier. If you remove the outlier beforehand, the remaining fit gets a lot better. And so if you can identify outlier points in a systematic and principled way, then you can potentially get a better fit for it. Any questions? There is a question of one problem with a linear fit, of a bunch of points, is by definition that it is linear. It only limits you to a line. But if you add other variables to your data matrix that represent nonlinear terms, you can fit nonlinear functions with linear regression. So for example, in this case, the green was a quadratic model. If all we start out with is a variable x and y, the best fit we get is this red line. That's a linear fit. But if we add a second variable to our matrix, which is going to be x squared, now we have, in some sense, three terms that we can fit. There is the linear term x, there is the quadratic term x squared, and there is the constant term 1. There's going to be three coefficients in that, and you can get a better fit to try to realize it. So linear regression can be used to fit nonlinear things, provided you are smart enough to identify what the nonlinear terms are. So if you know that if you look at your points and you think it's quadratic, and you add the x squared value, maybe you add the square root x value, the log x, x cubed 1 over x. You can add as many, if you have n points, how many extra functions can you potentially add to make a better fit? You have one variable to begin with. You have n points. You'd like to fit it as well as possible. How many functions can you meaningfully add if you have n endpoints that you're trying to fit? Okay, anyone? Theoretically, you could add n plus 1, n minus 1. Okay, and then it's still going to be a constrained problem, right? In general, you would want to ask fewer terms than that. But again, you have the freedom to add more nonlinear functions of your original variables, and this is a useful thing to be able to do. Okay? Any questions? And again, the challenge is that if you add an infinite number of nonlinear terms, you don't have enough data to support it, and you don't have and the number of nonlinear terms potentially grows very quickly if you really want to, there's an infinite number of nonlinear terms you could conceivably add. But if you know what the general trend of your model is, you can make it better by adding that variable. Any questions? Now, another thing that you could do is scale your variables in a linear way. Z-scores, as we have seen, are linear scalings of variables, right? Now, suppose we wanted to try to predict some property of a country as a function of its population size and the percentage of people in the country with PhDs. Okay? In the United States, you have 300 million people. In the United States, you have, I'm going to make this up, 2% of the people have PhDs. Okay? And you want to predict something like how many Nobel Prize winners the country will have. Okay? That seems like an almost reasonable thing to do. What is a problem when you're trying to come up with weights, okay? We are trying to compare one of the variables is population of a country, and the other one is the percentage of people with PhDs, okay? It's clear that these numbers are not commensurate in scale, right? Is this a problem when you try to fit? Let's say we're trying to predict the number of PhDs, of Nobel Prizes the country's won. How many Nobel Prizes has the country won? How many do you think the United States has won over its lifetime? Okay? I don't know, but I know where I would find it. Okay, turns out that outside the Museum of Natural History, there's a monument where all the American Nobel Prize winners are on. It's enough names that it sort of fills a decent-sized monument, but they're running out of space. So that probably means that there's maybe 100 or so Nobel Prize winners that were American so far. Okay? What do we know about C1 and C2 if we are trying to predict a target which is going to be about 100? What does C1 have to be? Very small. And what does C2 have to be? If it's going to be used, it better be very large. Does everybody agree with that? So one problem is that these things are over different magnitudes, okay? And that makes it kind of a weird thing. What happens if we replace the population size by a z-score and the PhD percentage by a z-score? What would be the means and values, the means of these things? Does everybody agree that the population mean would now be 0? And the PhD percentage mean would now be 0, right? And the variance would be 1 on each one of them. So the variables would be comparable in kind of magnitude and range, okay? So what's good about that? One thing is that you can now look at the coefficients C1 and C2 and get a sense of how important the variables are. If we use the unweighted variables, we all agree C1 was going to have to be very small and C2 was going to have to be very large, right? But if we use normalized variables, then the variables mean something that kind of are the same magnitude. Whether the coefficient is positive or negative makes it, will tell us something about it. The magnitudes will be comparable. So under these cases, it's certainly more interpretable if the variables were z-scores. Okay? Any questions about it? We're also going to talk in a few minutes about a numerical way using gradient descent search to solve linear regression problems. And linear regression, the numerical methods work better if the ranges of values does not go too far out of the way. Any questions? Actually, one last question. If you had to add a variable, a function, a nonlinear variable, if we wanted to predict the number of Nobel Prize winners, okay, that a country has had, as a function of, well, all we know is its population and the percentage of PhDs, can anyone think of a nonlinear term you should add to the matrix here? Okay? We want to try to predict how many PhDs, how many Nobel Prize winners a country is going to get. Can anyone come up with a nonlinear variable here that probably does a better job than what we would have here? Okay, this was population. This was percentage of PhDs.
Academic funding.
What? Academic funding maybe does something, but that's something not in our data matrix, right? You have to go figure that thing out. You can't do this now. Maybe you can say, give me a computer and I can Google it. But what if I only have these two numbers now? If I wanted to predict something about the number of PhDs, the number of Nobel Prize winners, can anyone come up with a nonlinear function of these two variables that probably does a better job? Because I do think, anyone have a proposal? The ratio? I would say the product of these two. Okay? What is the product of population times percentage of people who have PhDs? What is it? The number of PhDs. Okay? Would I think that correlates well with the number of, I can imagine a country, you could imagine a country of Stony Brook where everybody has a PhD, but there's nobody that is very few people that live there, right? That would be the situation here. You could imagine a country of no education, which was huge, but it didn't produce anybody who would be, getting a PhD. It's the product of these two that I think probably better would define the number of Nobel Prize winners. This is what I mean about adding nonlinear terms. It's a little bit about looking at this thing and saying what other things are there that you could add to the matrix that kind of capture what we're doing. And note that the product of these two is exactly a nonlinear term. Any questions? Okay, good. What other problem is there? Often there are variables that have power law distributions. Okay, you may have seen that in some of your modeling here. But you can imagine trying to predict how much education, okay, somebody's kid is going to get as a function of parental income. I have kids. Bill Gates have kids. My kids are going to get some education. his kids are going to get some education. I think his kids have mostly already got their education, right? What would be the function if you consider a model that's going to try to predict your years of education times income plus a fixed amount? Does everybody see that this model couldn't hope to give something sensible here? That's both sensible for me and you and sensible for Bill Gates. Because if Bill Gates' income is, 8, 9 orders of magnitude higher than ours, right? That would mean that C1 has got to be extremely small if it's going to keep the number of years in a range that a normal person would live. Okay? But if you add the log of income here, the log of Bill Gates' income is a number like 10 or 12 or something like that. The log of mine is, just to make, maybe it's a 5 or a 6. The log of yours is maybe a 1, okay? But does everybody see that this is now a range of possibilities that is at least commensurate with what our target is, okay? And this is why we needed to deal with power laws. Any questions? Okay, that was good. And often when you're trying to produce a target, like, okay, I'll admit I have my graduate students right now are working with social scientists in the Netherlands to try to predict people's income, okay? And based on other things, how much schooling they had, how much, where did they live, all kinds of stuff. Now, they don't predict income. They predict the log of income. And why is it? It's because income is, as we've seen, a power law thing. So if you try to predict, it's often more useful to have a nonlinear function of your target, not just a nonlinear function of your variable. And then these can produce more meaningful things. Any questions? I think people understand that. Okay. And again, it is often good to come up with an interpretable model for your variables to be z-scores and your target to be some kind of a z-score, just so that things are the proper kind of magnitude. We don't want large coefficients. If we have small coefficients and large targets, small variables and large targets, we need large coefficients. It's important to think about the scale of these things. Any questions? There is also the need, when you're coming up with a model, to try to avoid having highly correlated features. Okay? Suppose, let's say, you have your feature that is measuring, let's say, your the length of your left foot, the length of your right foot. These are going to be very highly correlated. What is the problem with highly correlated variables in a regression model? Well, one thing is that it tends to produce matrices which may not be full rank. Okay? More importantly is a question of how do you interpret them. Okay? If I have two variables that really are essentially, one is predictable from the other, is linearly related to the other, that's what correlated means. Okay? Then the question of how I should distribute the weight between these two variables is not defined. Okay? So how do I identify and get rid of highly correlated variables? You give you a bunch of data. You have a data set. You've got a bunch of points. Those are the rows. You've got a bunch of columns. How do I identify which variables are highly correlated? Okay. I could compute the pairwise correlation matrix of all the variables before I do my regression. I could compute the covariance matrices of this. That was also supposed to lead life onto this thing. And what do? Well, one is I can identify them explicitly and decide which ones go away. The other is to say if I have a situation where I have a lot of variables that are highly correlated or linearly related, this is the argument that I should be doing something like singular value decomposition, some form of a dimension reduction, to try to reduce the number of dimensions I'm giving my model. Any questions? Okay, I think we all understand this. Okay, good. So what I'd like to now talk about for the rest of the class is something about how you solve linear regression problems using the kind of machinery that we use for other machine learning algorithms, okay? Things like gradient descent search and regularization. So what is good or bad about that linear regression formulation, that linear algebra formulation of linear regression? The good thing is that the entire formula was, 5 or 6 characters long. Okay, it's a concise thing. It reduces it to, known things like matrix multiplication and inversion. What are the problems with solving linear regression that way? One is linear inversion is slow when you've got a large number of points. It's an n cubed thing, okay, where n is the number of rows. It's also a very brittle formulation. Maybe you believed, either when I talked about it or when you took linear algebra, that that particular product of matrices and inversions gave you the coefficients of the optimal line, okay? But if you want to generalize this to other ideas of what you want, okay? So right now we're trying to minimize linear regression, as we showed you, minimize the sum of squares. What if you wanted to minimize the sum of fourths? Okay? What if you wanted to minimize the sum of the absolute errors? Okay? These feel like different things, and it's no longer linear algebra can kind of do it. So, or at least linear algebra on the level that I can do it. And this kind of motivates the idea of a way of solving linear regression using gradient descent search, which I find much more understandable. Okay, and this I think is good to think about. So what is the idea with linear regression? With linear regression, we are trying to identify the values of parameters, the coefficients that we are going to weigh each column by in order to fit the target. So if we have a regression line we want to fit, W0 plus W1 times X, we have two coefficients, W0 and W1, we want to find. And if we want to do least squares, we want to find what are the coefficients that will minimize the sum of errors. If we define an error function or a loss function J, okay, the following loss function will describe the sum of squared errors. If we have n points, sum up over from 1 to n the difference of the target value of the ith point minus the result of our regression model, the prediction from our regression model, squared. Okay? The sum of these points is the sum of squared errors. Dividing it by 1 over n is the average sum of square error. If we minimize the total sum of error, sum of squares error, we minimize the sum of squares error, so this is not so very important. It's kind of a constant term. But what's interesting here, if we know how to find what are the coefficients W1 and W0 that minimize this, we know how to find the optimum regression line. Any questions? So what does this mean? This means that we can view lines, okay, regression lines, as points in parameter space. Here, a regression line, okay, the red line going through these points, okay. What if I fix the intercept to be y equals 0, then I've got a one parameter function, okay, where I have the error as a function of slope. That's what this picture is trying to show me. And when you get to the right slope, you minimize the error. Other values, okay, you get higher error. Okay? What's interesting about this way of modeling this is that the error function as a function of the slope and the intercept is a convex function, meaning that it has no local minima, and meaning that if you use a numerical procedure that will find the lowest point here, you will find the optimum, the lowest point in this W1, W2 space. Again, the z value here is going to be the loss. At any coefficient value, W0, W1, that is going to describe a regression line that will give you a certain error. You get an error surface here. The error surface that minimizes the error is the coefficient, gives you the coefficients of the best fitting line. Any questions about that? So what's great about this? What's great about this is that if you have a space where there is only one local/global minima, this is something called a convex space. What's great about it is if you want to find the lowest point in a convex space, all you have to do is from wherever you are, find a direction that goes down and take a step in that direction. Okay? If you keep going down, you will eventually hit the bottom, and that bottom will be the minima. Okay? And the fastest way down is kind of defined by the line between what is the ultimate point and where you are. Okay? The fastest direction down is defined by the slope or tangent at your particular point. Okay? What does this mean? Suppose you have a surface here, the blue surface B. If you are sitting at the blue surface, if you're sitting at point B, which is the direction to move that will get you down? Okay? One way to do it would be to take a point, a small delta x from there, okay? And compute what is the y of that point. Those 2 points will define a line, okay? That line is essentially the tangent line at B. Okay? And as the delta x, the change that you have used, okay, is small, delta x over delta y defines the slope. Numerically, if you're at a point and you want to figure out which way is up or down, the simplest thing is to just move a tiny bit in one direction and see whether it goes up or down. If you moved in this direction, it went up. If you moved in this direction, it was down. When I took calculus, this was kind of a numerical idea of how you would get an approximation to the slope or tangent at any point. It was just by using the infinitesimals. Okay? So you could do it numerically, or you could do it by partial derivatives. Okay? And the symbolic way of computing the gradient, okay, the fastest slope down, okay, for a point in a higher dimensional space is given by the vector of partial derivatives with respect to every variable. What was the partial derivative? Here, this is numerically, here was my loss function. If I took the partial derivative with respect to w, when I squared w, this would give me a w squared term, and a w times sx, and a w times minus b. When I took the derivative with respect to w, okay, the w terms, the coefficient went down from 1 to 0, and from the quadratic term went down from 1/2, from 2 to 1. That's why a w survives here. Bottom line is, if you take the partial derivative with respect to each of the variables, that gives you the direction to move down if this thing is a convex function. Any questions? That said, this gives us an algorithm now, gradient descent search, that will enable us to solve any linear regression model in any number of dimensions. Okay? Our model is going to have a certain number of dimensions. There's a target that we want, which is a linear equation. We want to know the coefficients. The loss function is the sum of squared errors given the current values of these coefficients. The hypothesis, there's the current values of theta, of the coefficients. The sum of the squared errors, or the average sum of the squared errors, is our loss function. What is our algorithm to proceed? We start at a random point in parameter space. We are then going to, at each iteration, compute the partial derivatives with respect to each dimension and move in the direction that will minimize, the partial derivative was going to be telling us what is the way down, what is the fastest way down, okay? We will know what is the rate of change as a function of each dimension. We're going to adjust each parameter by being the partial derivative of the loss function times some constant alpha, okay? And that will give us a new point. As we keep going, okay, we're going to converge and eventually hit the bottom of this convex shape, and that's going to be the optimal, the optimal coefficients of our linear model. Any questions? Now, what is good is that for linear regression, the error surface happens to be convex. What does convex mean? Convex means there's one local minimum. Okay? Now, what does it mean to have a local minimum? Okay? When I was taking calculus in one dimensions, okay, what did I know? Whenever the first derivative of my variable was 0, that meant that I hit a local minimum or maximum. And it was the second derivative that told me whether it was going to be, you know, a maximum or a minimum. Okay? So what we're really wanting to know is kind of to tell whether an error surface is convex, okay, is really a question of that's defined by the state of the derivatives, okay? If you looked at the set of derivatives on your, you know, the partial derivatives defining your surface, okay? An analysis of this will tell you whether your function is convex or not, okay? In one dimension, it was really a question of whether or not there was only one place where the derivative was 0. This gets more complicated in higher dimensions. There's things like saddle points and other weird things that can happen in surfaces. Okay? But bottom line is that analytically, certain error surfaces you can prove are convex. This is good because you know that you've got the optimum, okay, before you start if you do one of these things. If you don't have a convex error surface, the gradient descent can get trapped in a local optimum. Any questions about that? Okay. So what does it mean to get trapped in a local optimum? I think, suppose, let's say you are sitting at a, you know, you want to get to the top of a mountain to go skiing. If you are sitting in a lodge at the bottom of the mountain and you want to get to the top of the mountain, okay, if, you know, you walk outside and you walk up the hill, there's going to be a way to get to the top of the mountain. If, on the other hand, you go from the first floor of your lounge to your second floor of your lounge, now you've gotten higher, you've gotten closer to the mountain, but there's no way to get back to where you want to be without moving down. Okay? So the surface there is not convex. Many situations of non-convex things. If you get unlucky, doing gradient descent search will get you trapped in a local optima. But even in non-convex optimization, maybe if you started a couple of times from different random places, if you try to do gradient descent search, you'll get a pretty good answer. So numerically, gradient descent search only gives you the right solution if the thing is convex, but that doesn't mean that even in non-convex problems, this is a bad idea. Any questions? Okay. So what is the impact on our learning procedure as of this function alpha? If we look at our gradient descent search algorithm, we say that it is defined by the direction of movement given by the partial derivatives times an alpha value. This alpha value is going to be governing how much do we change the values of each of the coordinates of the points that we're at each iteration. In each iteration, we're going to take a maximum step size of alpha, okay, in the direction given by the partial derivatives. Now, if we use a very, very small alpha, okay, it will take many, many steps to get to the target. If we use a very, very big alpha, we might make rapid progress towards getting to the target, but we also have a chance that we will overshoot our goal, okay, and bypass and skip the real minima. So there is an art involved in trying to set this learning step size, or as it's often called, the learning rate. If the learning rate is too slow, too small, the optimization will take a long time to converge. If the learning rate is too high, we are in danger of overshooting the goal repeatedly and not actually finding the ultimate minima. Any questions? What is the right value of the learning rate? Well, this is sort of now becomes kind of a heuristic kind of a question. One argument, or the way to basically do it, is to monitor how the loss function is decreasing over time. If the decrease is too slow, then maybe you're going to want to increase the step size, maybe multiply it by 3. Okay? If the error starts getting larger instead of smaller, that certainly means the step size is too large. Maybe you need to decrease this. And so in practice, there's got to be a procedure to adjust the learning rate as the error goes by. And when you're doing machine learning, you often hear about something called an atom optimizer. This is one of the algorithms for adjusting the learning rate. Any questions? Okay. What is the good thing? So what is where do we sit? We know that the error in linear regression was the sum of squares. We know that it was constant. We know that it was convex. So we know that if we did a gradient descent search, what is the complexity of this step in the algorithm? Let's think about this for a second. Okay? If you want to take you have n points in d dimensions, and you're trying to find what is the partial derivative, okay, at your current point, what is the complexity of this iteration? Certainly in each step, we're going to be adjusting each one of the d parameters if your points are in d dimensions. So this thing is going to go around d times, certainly, for different theta 1, theta 2, theta 3. What is the complexity of this? What is the complexity of the loss function? Okay, the sum of squared errors. What? It's a function of the number of points that you have. I guess the number of points times the number of dimensions. Does everybody agree? So what's kind of hidden here that is expensive? The cost of computing the loss, okay, is going to be the size of your data set. Okay? And so if you really want to accurately determine what is the error, what is the direction to move in order to to make the fastest progress towards the goal, this is going to take time proportional to your entire input data, okay? Which on a large data set is expensive. So what is it that turns out to be the winning idea? The winning idea is, instead of estimating the gradient by taking all the training points, one possibility is to take a small number of your data points, maybe randomly sampled, maybe sampled in chunks, okay, and use that small number of points to estimate the derivative, and then hope that this is also going down, okay? The larger your batch size, the more accurately you're going to estimate the derivative, the more accurately you will know what is going down. The trouble is, it will then take more, but the So the larger the batch size, the more accurate the estimate. The trouble is that the more expensive the estimate is, and in the same time, the fewer number of steps you can take to go down. But if you optimize the learning rate and the batch size, it's actually kind of amazing how quickly you can optimize convex functions, okay, even in high dimensions, even with large numbers of points. Any questions about that? Yeah?
If the number of points are low, does the gradient descent achieve faster global minimum?
So if you have a small number of points, again, there is a trade-off between you're trying to get from here to someplace else, and you've got a trade-off, okay, of you want to move in the right direction, and you want to take steps as quickly as possible. So there is presumably there is a trade-off here. Now, if you have a very small number of examples, then the cost of computing the derivative, the exact derivative, is going to be cheap, okay, at any given point. So certainly for a small enough number of examples, your batch size will presumably be everything. But somehow there is a trade-off between these two things. I don't know if that answers.
But if let's say the step size is the same,
Yeah.
so the number of steps required would be lower with, let's say, 10 samples instead of 100 samples, right?
If the step size is the same, then, you know, if you have 10 samples, I mean a sample of 10 instead of a sample of all 100, you're going to be making 10 times as many steps in principle in the same time if you did a batch size of 10 rather than a batch size of 100.
No, but I'm not talking about the time required, I'm just talking about the number of steps required.
Well, if steps means the number of iterations, then the more accurate an estimate of which is the fastest way down, you're going to you'll use fewer iterations if you use a batch size of the entire data set. Right? You're trying to minimize the loss over the entire data set. If all you are counting is how many iterations, how many times does this loop go around, you will get faster. This loop will go around, will converge, will go around the fewer number of times when your batch size was n. Okay? On the other hand, you know, the total, it's going to be, the total running time is the number of iterations times the cost to compute the derivatives. If you spend 10 times the amount of time to compute each derivative, but you only save, it only cuts the number of steps in half, then you're better off using a batch. Okay? That's, I guess, the trade-off. Any questions? So, bottom line, the stochastic gradient descent, okay, is this idea of taking these random samples, and this is sort of the right thing to solve large problems in practice. Okay? Any questions?
But every iteration will take a new random sample, right?
Right. So in that case, the assumption would be in every iteration you're taking a new random sample or a not so random sample, a different chunk of the answer. Okay? Fair enough. Any questions? Okay. The last thing I'd like to talk about today that turns out to be important in linear regression is that often what will linear regression do? If you give it 100 variables to to target, okay? You're trying to predict y as a function of 100 variables. What is it going to do? It's going to come up with 100 coefficients, one to multiply each column by, to best fit what the target is. Now, sometimes we're not happy with the, a linear regression where we fit every, in a normal linear regression, if you give me 100 variables, I'm going to come up with 100 coefficients and best fit my target. Now, Occam's razor said that the simplest explanation is best. If we could come up with an explanation in 10 variables, okay, that does almost as good a fit as the one with 100 variables, maybe we're going to be wanting to have the simpler model be the one that we use, okay? In general, right now our optimization criteria for linear regression was only to minimize sum of squared error, okay? Ideally, there is a trade-off between the number of variables that we use, okay, and and the quality of the fit. And we would like to come up with a model such that it uses only the variables that are most important, okay? How could we do something like this? Just given, if I had a large number of variables, okay, and I wanted to come up with a linear regression in a small number of variables, how might I do that, just conceptually? Okay? What? So one would be dimensionality reduction, and that, as we saw it before, would have been a squeezing out of things. But that's probably not going to leave something that's very explainable. If all of these things were housing prices, let's say you were trying to predict the housing price, does it have a garage? Does it, how many bathrooms does it have? What's the area? What's the quality of the school district? If I did a dimensionality reduction, I'd end up with something with fewer dimensions. But the names of these things don't mean anything anymore. Okay? What would be a way that I would come up with a regression model that would be, use fewer variables but use the ones that count? What? So one possibility is to remove highly correlated variables. If I have two core variables that are really highly correlated, yes, maybe I could get rid of one and that would be fine. Okay, so one idea would be, what if I fit a regression to all the variables, but I properly had normalized all my variables by z-scores? That may be, what would happen? Then the coefficient of the variable is going to be a measure of how important it is. Do people kind of get that idea? If the variables, if I want to, say, how will you do in this class? I have your IQ, I have your weight, okay, and I have your IQ and your weight, okay, and if I had my IQs normalized, the mean was 0, weights normalized, the means were 0, what would happen, okay? What would happen is that the coefficient for IQ should be pretty high, and the coefficient for weight in an absolute sense is going to be very low. So one possibility would be to fit them and to throw out the variables that had small coefficients as being unimportant or have stuff that was explained elsewhere, and then refit it. This would have been a simple way to kind of do some kind of feature selection. Okay? But there's another more formal way of doing this kind of thing called regularization. With regularization, what is the idea? We're just going to change our loss function so that the loss is going to be a function of the error that we get, in this case the error of the difference between the prediction and the target, and add another term, okay, which tells us how well do we like the coefficient values that we normally have. Here, I'm going to add a loss term that's the sum of squares of each coefficient. If I want my coefficients to minimize this loss function, the coefficients now have to do two different things. One, it's got to do a good job of fitting the points. And two, it's also got to do it while keeping the absolute magnitudes of the coefficients small. Okay? By adding this regularization term, okay, I'm going to have a trade-off between how well do I want my fit versus how well behaved do I want my coefficients to be. Okay? And if the coefficients are 0, I don't get any error term here at all, but of course I'm going to get a bad thing fitting the points. Depending upon what this constant lambda is, it gives me a trade-off between the quality of fit and the quality of the coefficients. Okay? And this is regularization. Any questions about it? What's great about it? Okay? There are, again, if the variables all have mean 0, because they were like z-scores, the coefficient magnitude is a measure of how important they are. Okay? If we penalize the sum of squares of the coefficients, we get ridge regression. If we penalize the absolute value of those coefficients, we end up getting something called lasso regularization. But one way or another, okay, we get a, regularization adds something to the error term so as to shape the desired coefficients that we want. Now, this makes a difference. What happens when you get highly correlated variables in your input? Okay? Not perfectly correlated, but highly correlated. If you actually try to fit, suppose V1 and V2 are highly correlated, okay? You may end up getting, I often have seen, regression coefficients that look like this. A model that gives a high coefficient times 1 minus a slightly less high correlation coefficient times the other. Okay? These variables, because they are highly correlated, they're basically canceling each other out. Does everybody see that? If V1 and V2 were the same, just having the model y equals V1 is going to be better. Okay? And what the goal of regularization is to try to lure it away from models like that to models like this. Okay? Any question? The claim is that this kind of a model, okay, the second model is better even if it fits the training data slightly less well. Okay? That's the idea of regularization. Any questions about that? Okay? As it turns out, okay,